Hello everyone, my name is Biswas and I'll be posting tutorials related to wireless power transfer. That includes the coil design using the FEM tools like Ansys Maxwell and console multiphysics. These are the few chapters that I'm posting right now, and these will be followed up by other tutorials that are um, kind of a little bit harder in the sense of difficulty level. Uh, yeah, that's it. And without wasting any time, let's move forward to the simple coil design techniques. How we can achieve that thing in Ansys Maxwell simulation software. So if you are not familiar about the software, please have a look at that thing first, because you need to have prerequisites. Certain prerequisites are there. So before we proceed, make sure that you have installed the full-fledged version of the Ansys Maxwell. Not Ansys Maxwell actually, it's called Ansys Electronics Desktop. And under that, there are different packages, and one of the packages or module is the Ansys 3D, Ansys Maxwell 3D. So we'll be carrying forward with the Maxwell 3D component of that thing. So yeah, that's the software we are going to use. So please make sure that you have installed that correctly on your system. If you need any type of help or maybe the resources, then maybe I can help you. Please like mention me in the comment or just comment there, and I will be ready to help. Very glad to do that. Uh, and furthermore, if you want any other things, any recommendation, any suggestion regarding whatever I'm trying to prepare for you people, yeah, you can suggest me those things in comment section or directly mail me in the link in the mail that is provided in the description. Yeah, that's it, and let's start. Yeah, and another reason why I'm facing this side is my desktop is on this side of, so I have an external monitor, so please ignore that. And please ignore any background noises that come time and again. Let's proceed. And yeah, before we jump into the simulation part, first, what's the agenda is? The main agenda is that we're trying to, today, we are trying to actually design a coil that is particularly used as air core inductor. So if you have ever heard of air core inductor, then its basic uses is in high frequency applications. So yeah, so it looks like this. This is the helical structured air core inductor. So the stranded conductor is used here, and this one is a helical one. And similarly, this is the spiral coil. So the structure is like this, the spiral coil. So you have certain things to know before you design a spiral coil. Similarly, you have certain things to know before you design a helical coil. And this one, I would say, though it's known as a spiral coil, but I would suggest this is a deviation from the helical structure. And why I say this is because I'm going to show you in a few moments how this coil can be achieved from this helical structure just by changing the radius. So there is a parameter, there is a menu where you need to enter parameters, and there is a single parameter that is known as radius change. And when you change that thing, it actually converts to this coil. So yeah, basically that's the difference. And this is regarded as normally absolute spiral coil. The first one, this is regarded as a typical helical coil, and this one will be radius changed helical coil, at least for me for now. Yeah, having said that, and we'll move forward. So if you have, let's open the EDT. This is our electronics, Ansys Electronics desktop, and it is composed of different packages, as I said. So where to start for a beginner? This is completely new, and it might be very overwhelming for you people. Yeah, so because I'm targeting beginners who do not know anything at all, and yeah, I'm really sorry for this. Let me remove these things first, right? Uh, Let me remove the text now, and let me put myself in this position here, right here. Yeah, I guess I'm okay now, and I guess I do not disturb you people now. Yeah, it's fine. So basically what you can see in the screen is the output that we are going to design today. This is the coil that we are going to design. Have a look at it. So absorb this coil. This is a helical structure. So coil of one another. Uh, so yeah, we'll discuss this. So how to achieve this coil and how to simulate certain results, that is how to calculate the inductance of the coil, and many more things, right? So how to excite this coil, how to calculate inductance, and so on and so forth. So before we proceed, this is the first home screen that you'll get, and let me go to the file, and then there's new. This is what you will do for the first time, right? So without any hesitation, just go there and click that thing, and you will get a new project. Though I'm not going to do that because I have already made a project here. So these are two projects that I've already assigned here, right? If you do new, another project will come here as project one or project new, something like that. So this is what I have created. This is the project that I created. So I'm not doing that. You can do that from here. And then when the project is created, it's empty. Well, let me do for you. Create new project because it might be confusing sometimes. So yeah, this is how three projects got created here. So I have three projects now. So you might have only one project that's as named as project one, and then you will open that project, and you will see there's some builder, there's some folder, and you do not know what is that, right? So do not worry about that at all. Now, how we proceed is after you have created project, the first thing you will do is you must rename the project because it might be very confusing when you work on multiple projects. So that's the basic idea. Well, yeah, you can rename or just leave it like that for now. Now, next thing is because we are trying to design the coil with certain parameters, with certain physical constraints there, right? So first thing we'll do is this is EDT. Let me remind you again. And inside EDT, there are different types of packages, or you can say sub simulators, sub simulation softwares, and in them, among them, uh, we are choosing Maxwell 3D because that's where we work, right? There is another type like HFSS, and there is another like Simplorer, nowadays known as Twin Builder. So there are different multiple modules. So we are picking only Maxwell 3D. So make sure that there's Maxwell 3D correctly installed in your system in Ansys, and then you will right click this project and then you will insert a new project, which is the type of project you will define because there are different, as I already told you, HFSS 3D, 3D, sorry, and then there is a circuit design, netlist design, Maxwell 3D, which we are going to design today, and similarly there is Twin Builder. This is actually very famously known as Simplorer, Ansys Simplorer. So this is Twin Builder. If anyone is confused, then Twin Builder is nothing but it's simpler. So let's not get to that side of the story, and let's focus on our coil design first. So yeah, what we are going to do is insert Maxwell 3D. That's what we're going to do, and that will create Maxwell 3D, and you can see that change has taken place. You can read it here. Now the project one, inside project one, you have Maxwell 3D design one, and inside that 3D modeler is turned on, yeah, and that's inside Maxwell. So that is what we want to confirm. So if that is not looking exactly similar to this, then maybe your version is a little bit different, or maybe you have not installed the system correctly. So please make sure things are fine. And as you do that, here comes the Maxwell 3D design, and here comes the coordinate system. So again, we must rename this for the for not to confuse with other multiple projects that you work on or other multiple designs that you work on inside the project. So for that, I recommend to rename this if you are working. But for now, it's okay. And one thing that you notice is inside parentheses, there's something known as magnetostatic mentioned. That I didn't put it there, but it came automatically by in the default mode. So what's that magnetostatic exactly? It's solution type. So what solution type is, so to put it basically, there are different multiple ways you can actually analyze your simulation. So that's how it works. So let's begin then. So what we need is we need a coil. So how to draw the coil is obviously we must go to the draw right here in the menu, you can see, but we are not going to draw it manually because there's something that is automated and it's actually written in Python. So that thing we can generate automatically. So you need not to worry about that. If you are thinking that okay, you have to do it manually, then no, there are shortcuts for this. You go to user defined primitive and you go to segmented helix, because that's where we are interested in. As I've already told you, we are making helical coil, and we will go to polygon helix. And polygon helix has the parameter settings where you can change certain things to get the type of coil that you want. And this is probably the most uh, uh, the major observation that you need to do in the overall design. And it's not that difficult because the descriptions are already given here. If you can see and read, like the polygon segments, so you define 0 for circle. That is, if you need a circular helical structure, you will set that as 0, not as 4. So obviously, I do not want a triangular or rectangular kind of the wire cut. The cut of the wire is not rectangular. That's not what I want. It's not the square either, right? I want it to be circular. So that is why I will set that to 0. And then polygon radius is nothing but the wire diameter. So I'm using that as 3 mm for now. Sorry, the wire radius. Start helix radius is what I was actually referring to as. So in this figure, this radius, the inner radius, is known as start helix radius. Uh, so that is why okay, this can be confusing. Let's go to helix. This is the start helix radius. So why it is known as start helix radius is that because when we change the radius, when we turn on the option of radius change, it will convert to this coil. And in this coil, there are two radiuses. One is outer radius and one is inner radius. So the inner radius is known as the start radius. So that's what it means. Because and here probably the except so when we subtract the wire diameter, it's almost the same. So wire is not that thick. So yeah, you get the idea here, right? What I'm trying to convey. So start helix radius is needed to be set according to the cross section of the coil that you want. So normally, yeah, you will always know this thing, right? Because these are the design constants that you must know beforehand when you design the coil actually. So for now I have noted it must be 30 mm for me, but I'm trying to increase it to, let's say, 50 mm. 50 mm will be okay, that's 5 cm and it will be 10 cm diameter. Okay, okay, let's see. 50 mm, 50 mm, okay, that's fine. Radius change, yeah, this we must set to 0 in order to get the typical helical structure. If this is set to any other number greater than 0, it will actually result in spiral kind of a structure that I have shown you just now a few moments before. That is the kind of coil you will get. And pitch is nothing but the distance between the two turns. Well, this is the pitch, the gap between the two turns, right? So this is, so I'm not interested in it, so I'm trying to, but the thing is, but the surprise is, you can't set it to 0 like this. It must be, because why you can't set the pitch to 0 is it calculates in the absolute value. And when it calculates in the absolute value, actually what it means is when your radius is 3 mm and your pitch is 0, it means the wires are overlapping to one another in the simulation. Whereas in real, it doesn't happen. In real, when we imagine pitch 0, we means wires stick together, right? But in simulation, it doesn't happen that way. Maybe that some error is there. So what we need to do is we need to have at least double, that means the diameter, that is 6 mm. So it must be greater than 6 mm. So to fulfill that particular parameter value, what I will do is I will do 6. So it must be greater than 6. So I will do 6.01. I hope you have understood this thing, because here's a constant that we can't keep the pitch value less than the double of, that is, well, let's say not less than the diameter itself, or not even equal to the diameter of the wire. It must be greater than the diameter of the wire, and the diameter of wire is 6 mm. Therefore, we are keeping it 6.01 just to attach the turns one after another without any gap. So theoretically, the gap is 0.01 mm. That's very less. It's almost 0. And number of turns, we'll keep the number of turns to 25. Let's assume that. Because when you do a few things for the first time, you have to do hit and try. So you do not know what value, what will be the output, what values will be the output. So you can't compare things, right? So the first time you just do hit and run, or if you have some theoretical calculations, then you go on from that, and that's it. Segments per turn is a kind of, it's a maze it's a maze that is created in the coil, and it is used by the simulator to calculate the values. So let it be in the default side because it will be a lot quicker if it is in default. And if you try to increase that, it will do the fine tuning in the mesh, and then it will take a lot of time. So we are not doing that. So 25. So basically we change turns, pitch, radius of the wire, of the coil structure, cross section, number of turns. That's it. And we do OK. Now, sorry, depending on your configuration of your PC, it might take a few like moment and or two few minutes. Like, um, and let me remind you, I'm using a very low configuration laptop. It's just i3 processor with 4 gigs of RAM, and maybe you have better laptop than this. It will not take that much amount of time. So yeah, bear with me. It will be constructed within moments. And further, I'm using a lot of other stuffs. I'm using multiple monitor, and a lot of application are actually turned on in the background. That is why it's taking a lot of time, right? So yeah, the coil is constructed, but you can't see. I'll do the magic now, and you can see it. Well, the coil is there. If you can see, the coil is constructed, and well, this is not the end of the design though, but you can see it's beautiful and it's created, right? So this is the air core inductor that we try to design. Well, but the design is not complete, and why it's not complete, I will tell you that. So yeah, and another thing is, yeah, you can do the rotation from here, or you can simply do the scroll part, the scroll button. You click the scroll button and you yeah, go on with the movement, and you will learn how to do scrolling perfectly. Sorry, the rotation perfectly, because it takes a while to get the hang of it, and yeah, you will be pro in no time. So that's how it works. So I would recommend an external mouse, yeah, for that. And go to orientation, and here you can change the orientation to different views. Like I prefer isometric, and then fit all. That's how it changes. That's how we work. So these things you can learn within no time. So I'm not focusing on that too. So one thing you have noticed, now we have a lot of things here inside model. So the 3D component, that is what we are working on. The model that we just now created, and we will create few more models right now. So we tick mark here, check mark here, check mark here. So we are somewhere in the model section now, the second model section, right? So just keep the account of where we are right now. We are in the model section, and inside model we have solids. Yeah, of course this is a solid, and there inside it's called vacuum, and inside vacuum there are the structure, particularly this structure. Um, and it's vacuum because it's the name of material. So normally right now this coil is not a copper coil because we have not assigned, it's a vacuum. So the material is vacuum. It is regarding this coil as a vacuum structure. So we'll change that in a while. For now, let's focus on the coil, and let's rename this. Let's rename this. But how to rename this? Just click there, and you can see the properties. In the properties, it's not clear like here in the material. It's called vacuum. Okay, and before that, let's change the name, and let's call it Air Core Inductor, right? Okay, Air Core Inductor. That's how we rename, and then we change the material. So here it's not listed. So if it's not listed, what you're gonna do is you go to edit, and then it will open a dialog. I guess there's something wrong with my laptop right now. It's lagging a lot. Okay, now here we come and we type copper, and here's the copper. and I will select that. That's as simple as that. But let me remind you, if you have not installed things correctly, you won't see all these materials available here. Yeah, that happens. If that is happening with you right now, or if that happens to you, then please do not panic. Try installing another package from another source, or just try to give a shot with the original, not the cracked version, but the original Ansys. Yeah, the stable version of it, and there will be no problem at all. We just use the university's license, right? You can get that if your university is good enough. Like I'm using the university's license, right? So yeah, cover, and then we'll select OK. Now that material is set to cover. So air core inductor is covered. But the design is still not finished. We have a lot of things to do. So here comes the moment. This is the start point, let's say, and this is the end point. If you can see, it's here down here. So what we're going to do is we need to excite this coil to calculate values like inductance. So we can't do that without energizing the coil, right? So and the basic fundamental thing about simulation, like the uh, finite element analysis, is that we actually do this thing as if it were a real environment. So in a real environment, the surrounding is air, right? If we were working in a lab, your coil would be surrounded by air. That's another material. Air is also a material. So that material we need to pick from somewhere and actually surround this coil by air. So can we do that? So to do that, obviously it's open border. As you can see, if I see the top view and if I zoom out, you can see there's nothing. I can go on zooming out and there's nothing, right? So we can't do simulation in such an environment. So we need to have a certain constraint for the design, and that constraint is actually we need to create a virtual air environment, a vacuum, not say, let's not say vacuum, but a region under which our coil will be placed inside that region, and then we'll do the simulation as if it were in a real laboratory, right? If you get this, then yeah, let's move forward and create a region for this thing. So how we create a region is, normally you will see this isometric view. Let's zoom out a little bit so it will be easier. Now I need to surround this coil by a big region. Now how I'm going to do that is, there's a trick to it. So there are a lot of things you can do, right? The design process, so you can do this FEM analysis of the same thing by different ways, number of ways, but this method I prefer. And yeah, so let's move forward. I will go and change this to top view. When I change it to top view, it's very easy to actually see how big. So for the relative measure, it's good. Yeah, and another thing, if you want to measure the coil size like this diameter, you can do this by this scale. So it's around 100, right? Yeah, that is how you get to know about the size. That will be, that much huge will be your coil in diameter cross section. Now, yeah, now we are about to draw the region, and to draw the region, we'll take the cuboid from here. Yeah, you can see that, and I will count the squares. So 1 2 3. Let's zoom out. There's something wrong with my laptop today. It's not, so here actually the squares get displayed here too. So well, anyway, 1 2 3 4. So it's 200 mm. We'll go far again, 250. So you can see at this bar right here, it shows the box position in X, Y, and Z. Since we are viewing in X and Y axis in 2D, because we are on the top view right now, what we do is we actually set the X and Y values and not the Z value, remember. So we'll count for the better estimation, we'll count the boxes 1 2 3 4, 5 somewhere here, and that is leading 250. So it's kind of 250 mm actually, and I'll pull that from that corner to 1, 2, 3, 4, 5. That is giving kind of symmetric, and the total value in mm of the square is 500. You can see from the bar. I will click it once. Now if I move the mouse, it actually changes the direction, uh, in all the direction actually, the x, y and z. But since I'm in xy axis in 2D form, if I move the mouse, it will change the z direction only. So that means it's the height of the cuboid, if you are getting what I mean. So now another thing how to access, but when you move the mouse, the measurement is not precise. So to do the precise measurement, you press tab, the tab button in your keyboard. You press tab button. The first time it goes to dx, that is to change the x-axis. So you need to specify. Second tab you go to y, and third tab you go to z. And as I already said, we are on xy axis, and already we have assigned the x values and y values. But what remains is the height of it. So to assign the height, that is the z direction, you can assign it in negative z direction or positive z direction, it doesn't matter, right? But we need to assign the real length of it, the real height of it. So for that, I press tab and I went to the DZ portion, and there I will input, let's say 500, yeah, 500 mm, and after entering 500, I will just press enter. That's it. You won't see that much of change, but what happened just now is actually it created a cuboid of height 500 mm. Now, since we are in the top view, we are not able to see exactly how long is that, how high is that cuboid, but now we'll change the direction, sorry, the view. Now we'll see the front view now. Yeah, now it had changed, and do the fit all. Yeah, and zoom out a little bit, but you can't see that clearly, right? So what you do is you click on this object and you go here, down here somewhere there is transparent. So transparency setting must be set to 100% transparent, and that will be easy to observe now. So this outer line is of the cuboid. This is how it is being placed. So from the 0th coordinate, it starts its height. So yeah, it's actually, sorry, it's actually surrounded by the cuboid. That's good, but the height is not that much uniform. So the coil must be somewhere in the middle. And since the height is 500 mm, we'll try to shift it down by 250, and it will be somewhere in the middle. That will do just fine, right? So let's shift the cuboid to the negative z axis by 250. To do that, you click on the cuboid and the highlight goes to box 1. So the name of that cuboid is box 1, and then you create on the you click on the create box, and then this property here, there are the values that we have set already. So you can change those values from here to the x size, y size and z size. That was 500, 500, 500 as we did earlier. And then the position is 250, 250. But what we'll change is we'll not change x, y, but z, the position of z, because the position of z actually started from 0 by default, but we gave the height, not the position. Remember, we gave the height at z size. That's a z size, it's different. Now we are trying to give position, so it will shift the cuboid in the z axis. So for that we'll do minus 250. You can see the change, it actually jumped below. So fit all, zoom out and see. Yeah, if you think that, well, the coil is exactly not at middle, because the coil also starts its journey from 0 position to the upper position, you can actually shift the cuboid a little bit more if you feel so. So I will do 150, probably that's good, or maybe not. Let's see. Well, yeah, that doesn't matter that much. Now, uh, the surprising thing is the simulation will be more like it will be better if you make this cuboid as large as possible, because that's how a real laboratory environment is, right? because it's completely surrounded by air to far lengths, right? So if you can do that, try to make it like infinite, and that will be good. But on the other hand, it will take a lot of time to calculate the mass and to actually simulate the thing. So here we assume this much space is actually enough. So this space now will be filled with air because we'll assign the material as air, and it creates a virtual environment. So it's an air core inductor. Yeah, that's what we are trying to establish. Well, you have understood that now. So let's go ahead and assign this material inside the box, or the box, define the box as air material. Let's do that. Click in that. So it's a box. It's vacuum now, but we do not want vacuum. We actually want to change this to okay, not available. Go to edit. Let's wait. Go there. Type air. So yeah, all the properties will be assigned. So it has now converted to air. Yeah, that's done. Change the view back to isometric because it's done. Fit all, and you can see your coil. But I'm really sorry to say that design is still not complete. There are lots of things to do. Now, what's that? Let's move forward. But I guess that's too lengthy video to make. So I will continue from here in the next video. Thank you for listening and enjoying the tutorial. Thank you. And yeah, do not forget to subscribe and give a thumbs up. Thank you.